Okay, we're back with our series of videos looking at different classes of functions, and this video is going to quickly go over some of the properties of rational functions. Now, rational functions by definition are the quotient of two polynomial functions. So the formula for a rational function looks like f of x equals p of x over q of x, where p of x and q of x are both polynomials. So for example, then the top would be some a sub n times x to the n plus a sub n minus 1 x times x to the n minus 1 and so forth. And similarly for the denominator. The leading coefficient in the numerator and the denominator could have different powers, could be the same power. Some of these coefficients could be 0, but we have this here, and this is our rational function. Notice that rational functions actually do include polynomial functions because you could let the denominator be 1. So certainly rational functions include some continuous functions. And in fact, rational functions are actually continuous everywhere they're defined. But they have discontinuities where they're undefined, of course, and that can happen. And the only place it can happen is where the denominator is 0, because polynomials, as we know, are defined and continuous everywhere. So the numerator and denominator separately are always defined. It's only in the division that you could have a difficulty, and that's when you divide by 0. So anything that makes the denominator 0 is going to make the whole thing undefined. So to prove that they're continuous where they're defined, we can just use some properties of limits and properties of continuous functions that we've already looked at. So if f of x is a rational function, by definition there exist these polynomials p and q, where f of x is p of x over q of x. And note that f of x is undefined when q of x equals 0, so those x values are discontinuities. Now suppose x is chosen so that q of x is not equal to 0. Okay, not equal to 0. Then by the laws of limits and continuity of polynomial functions, we see the limit as x approaches c of f of x is the limit of p of x over q of x, which is limit of p of x over limit of q of x, provided both these limits exist and are defined. Well, since they're polynomials, not only do they exist, each of these limits exist here, and we get they're actually continuous functions, so we can find the limit by just substituting in c for x. That's p of c and q of c. And of course this is true unless we are dividing by 0, but we've already eliminated that possibility. So when we're so p of c over q of c is f of c, and so we see that rational functions are continuous at the points where they're defined. But of course the points where they're undefined are discontinuities, and if it has places where it's undefined, then in fact the graph has a break there of some kind. And it's actually, they're of two kinds. They're always either vertical asymptotes or hole in the graph. So the question then becomes, how do we tell the difference between a vertical asymptote and a hole in the graph? So first of all, some of these don't have either one. Certainly polynomials are continuous everywhere, but there are certain polynomials that you might have in the bottom, besides just a constant polynomial, which are always non-zero. For example, you could just have, say, x squared plus 1 in the denominator. That's always positive. So that type of rational function, no matter what's in the top, if you have x squared plus 1 in the bottom, for example, then and that's all in the denominator, then that would be a continuous function. But other times we have things that make the denominator 0, and those will definitely be places where the function is undefined. So how do you go about working with these? Well, what you do is you factor these out. You factor out the numerator and the denominator, but don't cancel anything out yet. After you've factored out the numerator and denominator, look at the denominator, see what x's make each of those factors 0. Those are going to be the things that are not in the domain, and those x values are going to be either vertical asymptotes or holes in the graph. Then reduce by canceling out factors in the top and bottom in the numerator and denominator that match. That's using the fundamental property of equivalence property for fractions, and we can remove that as long as that factor is not 0. Now that gives you a reduced version that's going to be the same except for places where the factors you removed are equal to 0. Now, if you take an x value and you plug it in the denominator and it's still 0 in the reduced version, then that x value is going to give you a vertical asymptote. Whereas if you plug in an x value and you add the reduced version and you get a value out, but it originally gave you 0 over 0, then that x value is going to be the x value of the hole in the graph, and the value that you get out of the output of the reduced version will be the y-coordinate of that hole in the graph. And of course, if you plug in the plug in the original formula as it's given to you for like y1 in your calculator, and then y2 plug in the reduced version, the factored and reduced version. If those two are equal everywhere in the table, then you know you did the simplification right. But if you see a place where they're all the same except for one place, then that place will be a hole in the graph. What's going to happen is the one place it's the original function will say error or undefined, be an error message, and then when you do that, then the other one will be the reduced version will, the original will say error, and the reduced version will actually have a y value there, and that y value is the y value of the hole. And of course, the x value that goes with that is the place where we have our discontinuity, our removable discontinuity or hole in the graph. But if they're both errors in the reduced and the original, then that's an x-coordinate for vertical asymptote. Of course, when you graph it, you should be able to see the vertical asymptotes fairly easily on the graph. Holes in the graphs are kind of hard to see. Like on a graphing calculator, you probably won't see them visually on the graph itself. Okay, so be sure you know how to do this, because you'd hate for somebody to say you don't know your asymptote from a hole in the graph, and so if you learn this, nobody can say that. So even though rational functions are continuous at every point in their domain, many of them are not continuous functions because their domain is not one connected interval. Let's look at, the next thing we'll look at is end behavior. If you want to take the limit as x goes to infinity or to minus infinity, it turns out that if you have a horizontal asymptote, if you have an actual limit, it will be the same on both ends when you have a rational function. That's not necessarily true of other types of functions. For example, exponential functions have an asymptote on one end and none on the other end. Logistics functions have asymptotes on both ends, but they're not the same value. So, but for rational functions, if it has a horizontal asymptote, it will be the same value on both ends. Now, the easy way to find the end behavior is notice this feature that we noticed before about polynomial functions, is that, let's just look at the polynomial function at the top. We found that the relative size of these terms, if we think of these terms one at a time, the biggest power term dominates. Now, what we mean by that is if you were just to graph, say, y equals, let's say if you were to graph y equals x cubed and y equals x squared. Okay, they cross each other at 1, 1, but as you go further and further to the right, there's more and more space between them, with the x cubed getting further and further and further away from the y equals x squared. So if you were to graph that and zoom way out, then eventually the x squared would be so far down close to the x-axis compared to the x cubed that it really doesn't, it certainly affects the graph, but not the basic shape of it. So the basic shape on the ends, that is, you go far enough to the right or left, is determined by this first term. Well, that same thing is true for the denominator. So it turns out if you just ignore all of these terms here, you get the same limit is going to infinity as what you get by these first two terms. First term in the numerator and denominator. So if you just take the an times x to the n over bm x to the m, that fraction of those two things turns out to reduce to an over bm, right here underlined in blue. That turns out to be an over bm times x to the n minus m. Now that's just a power function. Now if that power function is a positive power function, that would happen when the numerator is larger than the denominator, then we know that a power function like that will either go off to infinity or minus infinity on the ends, and this will have the same basic behavior as the original rational function on the ends. maybe nothing like it at all in the middle, but on the ends, far to the right, far to the left, those limits as x goes to infinity and limits as x goes to minus infinity will be the same thing. So it will not have a horizontal asymptote. However, if the power is bigger in the denominator, then this difference here gives you a negative power, and we know that all the negative powers approach the x-axis as we go out to the right and out to the left. And so the negative power functions do that. And so we know that the limit as x goes to infinity or minus infinity is a horizontal asymptote of 0. That's this one here. This one right here, the case A. And so the horizontal asymptote is y equals 0 on the far right and far left. Now, if the degree is the same in the numerator and denominator, where m equals n, then this becomes x to the 0, which is just 1, for x is bigger than 0. And so what you get is a constant out of this, a constant function, which is the ratio of those leading coefficients, and that becomes the value of your horizontal asymptote. So, for example, if the first term in the top was 5x squared and the first term in the bottom was 2x squared, then the whole thing would go to y equals 5 halves, would be the limit as x goes to infinity and the limit as x goes to negative infinity. And so that's a horizontal asymptote. Now, once again, as always, I refer you to my notes and videos in the algebra section of YouTube, of my YouTube videos, and look at the videos. There are a couple of them there on rational functions. If you can look at those, you're going to see a lot more detail about this. I developed this material a lot more slowly and carefully, but here's just a really quick overview of this. Now, let's close by looking at an example. And again, in those notes and videos, you're going to see many more examples and some more interesting things that can happen. But here's one example. So here we have 2x squared minus 8 over x squared plus 5x plus 6. So the first thing we want to do is factor. In the top, we can factor out a 2, and then we get x squared minus 4. X squared minus 4 factors as x plus 2 and x minus 2. And x squared plus 5x plus 6 factors as x plus 2 times x plus 3. Do not cancel at this point. So at this point, we can see by looking at the denominator that if x is negative 2 or x is negative 3, then we're dividing by 0, and that's, of course, not allowed. So the domain is all real numbers except for negative 2 and negative 3. So this funny-looking R is the symbol for all real numbers. Then you either see a backslash or subtraction sign for set subtraction, and then we subtract out these two values. That's the easiest way to write that, the most compact way. Now, then look back at that and see that when x equals negative 2 and x equals negative 3, if we draw vertical lines at those two places, the graph will definitely not touch those because they're not in the domain. The function's undefined there. But if we take that, how it approaches those two lines is very different. One actually turns out to be a vertical asymptote. The other one turns out to give us a hole in the graph. Now again, how can we tell our asymptote from a hole in the graph? Well, we look back here and we see that this x plus 2 can cancel out as long as x is not negative 2. So if that cancels out, we get a reduced version of 2 times x minus 2 over x plus 3. We need to put this caveat, though, that x cannot be negative 2 here. Of course, x cannot be negative 3, but that's still implied by the new one. But there's no reason why in this formula by itself x couldn't be negative 2. And in fact, if you plug in negative 2 here, let's see what happens. Negative 2 plus 3 is 1. Negative 2 minus 2 is negative 4 times 2 is negative 8. Negative 8 divided by 1 is negative 8. You actually get a value out. If you put this in your calculator for y2, say, then you plug in negative 2 in the table, you'll see negative 8 come out, even though the original one will give you an error message. So that says at this point negative 2, negative 8 is a hole in the graph. In other words, the limit as x approaches negative 2 of this function is negative 8. Now, if we look at our vertical asymptote, that's going to happen when x equals negative 3, because if you plug in negative 3 in the original or in the reduced version, even in the reduced version, it still makes the denominator 0. So we know that is going to give us, still gives us dividing by 0. So x equals negative 3 turns out to be a vertical asymptote. That's sort of that form, constant divided by 0. Now you have to kind of look to see from which side it goes towards minus infinity, which side it goes towards positive infinity. Maybe it does one of both. In this case, I think it does one side goes up and one side goes down. Now what about the end behavior? Well, our little shortcut rule said if you look back at the original version, if you ignore all the smaller terms and just do the top power terms, the leading terms in the numerator and denominator, we get 2x squared over x squared, which just reduces to 2. And so the polynomial, the power function p of x equals 2, or the constant function p of x equals 2, which of course is the horizontal line y equals 2, will tell you what's happening on the extreme right and left. So the limit as x goes to infinity of this function is 2, and the limit as x goes to minus infinity is also 2. A couple other things, if we want to find the y-intercept, we just plug in x is 0. All these three terms go to 0, and you just look at the constant terms here. Negative 8 over 6 reduces to negative 4/3. So 0, negative 4/3 is, of course, the one and only y-intercept. The x-intercepts, let's see, this is going to be when the numerator is 0 in the reduced version. So look at the reduced version and see what makes the numerator 0, and we see the only place is when x is 2. So x is 2, y is 0, and that's got a power 1 up there, so that's a multiplicity 1 root. So it should go through the axis, x-axis there, and to the other side, kind of like it's a straight line, kind of just going through. So the same thing we learned about polynomial functions, the way the roots look is similar for these here. In fact, between the holes and the vertical asymptotes, the graph is similar to a polynomial function. It's smooth and continuous. Okay, let's take a look now at the graph here. So here's a graph. You're not going to see the hole on here, so we would need to put that in. Okay, but here's a computer-generated graph that did not show the hole. And looking at some x and y values here. Of course, this is x. This is the original y's. These are the y's on the reduced version. Of course, they all match up. Notice that both at negative 3, we get an error message on both. That's going to be the vertical asymptote right here. And at negative 2, however, you see negative 2, negative 8 is a point on the reduced, but it's not on the original. So there's your hole in the graph. I need a probably better scale here to see that, but negative 2, negative 8 is going to be somewhere about where I've got my cursor right there, if you can see it. So somewhere about there is going to be a hole in the graph. So this graph has two discontinuities at negative 2 and then at negative 3. And so it's in 3 pieces. There's a continuous piece here that's concave up increasing. There's a break at the vertical asymptote. So the limit from the left goes to infinity. And the limit from the right goes to minus infinity as we're approaching negative 3. And then the limit as x approaches negative 2 is negative 8. So there's your hole in the graph right there. So we have a break there. And otherwise this part here is increasing concave down, and the whole thing going out far enough to the outside approaches a horizontal line. Now again, there's many other examples of this. These things can get a lot more interesting looking at the graphs. So I encourage you to look through my rest of my YouTube videos on rational functions in the algebra videos, and I think you'll find that that they'll give you some interesting graphs to look at. In particular, the rational functions section is a good one to look at when you're studying limits, because there's some interesting things happening with the difference between a hole in the graph where it actually has a limit and a vertical asymptote where there is no limit, and then the limits as you go to infinity give you the horizontal asymptotes when they exist. So some interesting things are there to study about limits with rational functions.